Hello, and welcome to the Xilinx training on packaging and integration of RTL IP for Amazon AWS F1. In this training, you will learn how to adapt your RTL IP to meet the interface requirements of the RTL kernel, how to assemble a complete hardware platform with the RTL kernels using the SDAccel environment and tools, and how to build an FPGA bitstream and then generate an AFI or Amazon FPGA image from the bitstream for AWS F1. We'll start by talking about the AWS F1 system and the programming model to interface the RTL kernel such that it can be integrated into a system. We will look at the interface requirements that the RTL kernel must meet so that it can be easily integrated with the F1 shell. We'll see how the RTL Kernel Wizard can help with the kernel creation process. And finally, how to build the FPGA image for AWS F1 from the RTL kernels. Here's a high-level view of an AWS F1 system. The system consists of the x86 host CPU that communicates with the Xilinx FPGA through the PCIe interface. The x86 host CPU runs the custom application and accesses the accelerator kernels on the FPGA through an OpenCL API. The runtime handles the scheduling of the kernels, passing data between the CPU and the kernel, and handling error conditions. On the FPGA side, you have the custom kernels, which are built on top of the AXI interfaces, DDR memory controllers, and PCIe DMA, which are the hardware platform blocks that enable the kernel to talk to the x86 CPU. The AWS F1 shell facilitates the kernels talking to the memory and the host CPU via the PCIe. It provides a thin layer of glue logic that is not differentiating and thus allowing you to focus on the acceleration logic in the kernel. The shell exposes clocks, resets, AXI connections, providing a standard interface for communicating with the system. The kernel has to comply with the AXI protocols and meet the clock and reset requirements of the system. Once the system has been built, the accelerator kernel, along with the AWS F1 shell, are synthesized together to produce the bitstream for the FPGA. SDAccel is the tool provided by Xilinx that helps manage the application being built. SDAccel takes the kernels, which have been packaged into XO files, as an input. The XO file is a container format that contains the kernel accelerator, metadata, and other information that is used by SDAccel when assembling the complete FPGA platform. This allows the host application to reference the XO files for acceleration kernels when compiling the system. SDAccel helps manage linking the kernels with the F1 shell and the host application. Once SDAccel has integrated the kernels with the F1 shell, it runs synthesis and place and route on the fully assembled design. Finally, SDAccel produces a bitstream in the form of a .xelbin file that runs on the FPGA. Let's talk about the kernel now, specifically the programming paradigm of the kernel. This will provide a model for understanding how the host application software views the kernel accelerator. So on the left, you see the function prototype for the RTL kernel with the C function arguments and the argument types. This is the view of the kernel in the host software. On the right is the hardware view of the RTL kernel, with the specific hardware port types that map to the C functions in software. All scalar arguments are passed to the RTL kernel through the AXI-Lite slave interface. The RTL kernel needs an AXI memory mapped master port for pointer arguments that are passed to it. It is important to note that the scalar arguments can only be inputs to the RTL kernel. These are written to the register file in the kernel via the AXI-Lite interface. If the kernel needs to return any values as outputs, they need to be passed through the AXI master interface using pointer arguments. The pointer arguments are used for both inputs and outputs. The data is passed between the host application and the kernel by reading and writing to the global memory. The kernel is able to access the data in the global memory through the AXI4 master interface using the base address of the memory that was provided via the AXI-Lite interface. The AXI-Lite interface is also used to control the kernel execution, including starting the kernel and checking the status of the kernel execution. Now we'll take a look at the specific interface requirements of the kernel, such that it can be easily integrated into the AWS F1 Shell using SDAccel tools. The three key interfaces that are required for an RTL kernel, such that they can be integrated with the F1 Shell, are clock and reset, an AXI-Lite slave interface, and one or more AXI memory map master interfaces. Let's look at the requirements for each of these interface types. The RTL kernel must have a primary clock and reset ports that match the names that are shown in the table. The AXI interfaces of the kernel are clocked by the rising edge of the clock, AP clock. The AP reset is an active low reset that is synchronous in the AP clock domain. The kernel may also have a secondary clock and reset port with the names shown in the table. This optional secondary clock supports independent clock frequency scaling and is independent from the primary clock. The second clock is useful if the kernel clock needs to be run at a faster or slower rate than the AXI4 interface. By designing with multiple clocks, proper clock domain crossing techniques must be used to ensure data integrity across all clock frequency scenarios. The RTL kernel must have a single AXI-Lite slave interface. This is the interface through which the host application controls the kernel. The host application can start kernel execution, monitor status, pass scalar arguments to the kernel, and write the base address of the global memory of the pointer arguments. The basic kernel control through the register at address 0 is performed by writing to the start bit, which is bit 0, and checking the status by reading the done bit, which is bit 1, and the idle bit, which is bit 2. The runtime will write 1 to bit 0 to start the kernel. And then when the kernel is done, it will write 1 to bit 1. If you use the RTL Kernel Wizard, this interface is generated automatically. We will talk about the wizard in the coming slides. In a typical host code execution, the host code sets kernel arguments, triggering writes on the AXI-Lite slave interface, after which the host code triggers kernel execution, writing 1 at base address 0 and starting the kernel. The host code then polls the kernel for completion, reading bit 1 until it indicates done. The RTL kernel can have 1 to 16 memory mapped interfaces. The base address of the data in the global memory is provided through the AXI-Lite interface by the host application. The AXI master interfaces must all be 64-bit addresses, as the DDR memory can be large. In general, you'll want to minimize the number of memory mapped interfaces that the kernel uses. The decision on the number of AXI master ports will depend on the performance and bandwidth requirements of the design. The recommendation is to have one AXI master interface for each required DDR channel in the design. Note that AXI masters must not use wrap or fixed burst types and must not use narrow sub-size bursts, meaning that the size should match the width of the AXI data buses. Let's take a look at a simple example design that has a scalar input param and a pointer value. In this case, the host will first write into the DDR global memory with the data that will be accessed by the kernel at a certain base address. The host will then write the base address of A in the register file of the kernel through its AXI-Lite interface. The host will then start the kernel by writing 1 in the control register of the register file. Once the kernel starts execution, it can now initiate access in the global memory at base address of A to read values of A and process them. And when it's done, it can then write the data back to the location in the global memory. We will now look at how we can simplify the process of meeting the kernel interface requirements by using the RTL Kernel Wizard, which is available in SDAccel. The RTL Kernel Wizard automates some of the steps that need to be taken to ensure that the RTL IP is packaged into a kernel that can be integrated into a system in SDAccel. Based on the interface information provided to the Kernel Wizard, it generates an RTL wrapper for the kernel that meets the RTL kernel interface requirements. The wizard automatically generates the AXI-Lite interface module, including the control logic and register file. The AXI-Lite interface module is included in the generated top-level RTL kernel wrapper. The wrapper also includes an example kernel IP module, which should be replaced by your RTL IP design. RTL IP developers will need to ensure correct connectivity between the RTL IP and the wrapper template. The wizard also generates a Vivado project for the top-level RTL kernel wrapper and the generated file. This enables working in the Vivado environment to update and optimize the RTL kernel. The generated files include a simple testbench for the generated RTL kernel wrapper and a sample host code to exercise the example RTL kernel. The example testbench and host code will need to be modified to test the actual RTL IP. The RTL Kernel Wizard takes in the RTL port information and information about the host function arguments as inputs. From this information, it produces an RTL wrapper for the kernel top level along with scripts, an RTL testbench for the wrapper, a Vivado project to work on the RTL and check synthesis results, and main.c sample host code to exercise the example kernel. The RTL IP can now be integrated into the generated RTL wrapper. And the final RTL is then packaged in Vivado into a .xo kernel container. Now let's go through the steps in the RTL Kernel Wizard. The wizard can be invoked from the SDAccel GUI from the Xilinx menu by selecting Create RTL Kernel option. This will bring up a separate window for the RTL Kernel Wizard. The Kernel Wizard can also be invoked from Vivado. The Kernel Wizard will take you through 5 pages. The first page contains an introduction and usage information on the Kernel Wizard. The following pages allows you to provide RTL name and clock information, scalar input arguments, specifications of the AXI masters. And finally, the wizard will display a summary of the RTL kernel. Let's look at these in detail. On the second page, you will specify the kernel identification information, including the kernel name, vendor, and library. You'll also specify the number of clocks. The kernel name is the name of the IP, which is also your top-level module name for the RTL kernel. It's also the name of the C function call for the kernel from the host code. Thus, it must be unique and conform to C and Verilog identifier naming rules. The kernel vendor and kernel library provide the name of the vendor and library used in the VLNV, and it must conform to the same identifier rules as the kernel name. The number of clocks determines if the kernel has a secondary clock in addition to the primary clock called AP clock. When the number of clocks is 2, a secondary clock and reset are provided to be used by the kernel. Now we'll specify the scalar inputs to the RTL kernel. Start by specifying the number of scalar input arguments that need to be passed to the kernel. For each of the number specified, a table row is generated that allows customization of the argument name and argument type. Then provide the name of each of the scalar inputs. The argument name is used in the generated Verilog control register module. Each argument is assigned an ID value. This ID is used to access the argument from the host software. Also, specify the data type for each of the arguments that is supported by OpenCL. The data type will affect the width of the control register in the generated Verilog module. Finally, we'll define the memory mapped interface to the RTL kernel. First, we'll specify the number of AXI master interfaces present in the kernel. A maximum of 16 interfaces may be specified. For each interface, we'll provide the interface name, data width, and the number of arguments associated with each AXI master interface. The argument name is the pointer argument to the C function. It's used in the generated Verilog control register module as an output signal. Again, each argument is assigned an ID value that's used in the host software to access the argument. Each AXI interface may be connected to one or more memory controllers. The system performance and bandwidth requirements of the design should be considered when determining the memory architecture and sharing of AXI master ports between kernel arguments. Once you've provided all of the information, a summary page shows the software function prototype and hardware control registers created from the options selected in the previous page. The function prototype shows what the kernel call would look like if it was a C function. The register map shows the relationship between the host software ID, which is used to access the argument from the host software, the argument names, which are the scalar and pointer arguments that we defined earlier, the generated register offsets, the data type, and the associated interface. Once we verify the correctness of the information in the summary page, we'll go ahead and click OK. This will bring up a Vivado project with all of the generated output files. Now let's look at the outputs generated by the RTL Kernel Wizard. So the outputs include the RTL Kernel Wrapper with an example kernel, RTL Testbench, Vivado project, and a sample main.c host code. The RTL Kernel Wizard generates a top-level wrapper that meets the interface requirements of the RTL kernel. As shown in the diagram, the wrapper includes an AXI-Lite slave module and a register file. This is where you will instantiate your RTL IP. The top-level RTL instantiates an AXI-Lite control module, which is generated by the RTL Kernel Wizard. This includes custom AXI-Lite logic and register file that is automatically generated for you based on the information provided in the Kernel Wizard. The wizard also generates a working example with the same function interface that we defined in the RTL Kernel Wizard. The generated example is a simple add1 function that reads a number of words from the memory through the AXI interface, adds 1 to the values, and writes it back to memory. The example design connects to the AXI master interface that was defined. You can modify the generated example code and insert your own RTL IP. Additionally, the Kernel Wizard provides an RTL Testbench for the example kernel that was generated. The Testbench provides a stimulus to drive the inputs to the RTL kernel example. The clock and reset ports are connected to the clock and reset generator in the Testbench. The Testbench will pass the input parameters through the AXI-Lite interface, shown on the left, and start the kernel by writing to the control register. It will drive sample traffic on the AXI master ports on the right. The full UVM environment is provided for you to enhance the Testbench and coverage and perform full functional verification on your design. Once we click OK, once you have confirmed the information provided in the summary page of the RTL Kernel Wizard, it will create and bring up a Vivado project for the example design. The project has the RTL Kernel Wrapper as the top level and contains all of the generated RTL code and the RTL Testbench. This is a complete RTL design and verification environment from which you can make changes to your RTL code, run RTL simulations on your design, synthesize your design, and analyze timing and area reports, and optimize your design. Once you have replaced the example RTL kernel with your actual RTL IP, perform complete verification of your design in the standalone Vivado environment. Once you're ready to build and package the RTL kernel for SDAccel, go ahead and click on the Generate RTL Kernel button on the top of the Vivado project window. The RTL Kernel Wizard also generates a main.c file. This is a sample host application code that can be compiled and linked with the example kernel in the SDAccel environment. The sample host template will set up the platform, execute the accelerator, and perform any post-processing after the accelerator completes execution. You can modify this code and adapt it to exercise your custom RTL kernel. We'll not go into the details of the host application code here. The training module on running the host application with the RTL kernel will cover OpenCL and host code development. When you replace the example RTL with your custom RTL IP, you may need to add some adapters or glue logic to achieve the desired connectivity. Once you have completed the design and verification of your RTL kernel, you're now ready to package the kernel into a kernel container file, or the .xo file for SDAccel. The packaging step is performed by clicking the Generate RTL Kernel button in the Vivado GUI. The XO file that is generated is a container file for the RTL kernel and includes the needed RTL files and other information that will be used by SDAccel to integrate the RTL kernel in the platform. SDAccel compiles and links the XO file into the platform. The compiled application can then be run on the physical hardware or using the hardware emulation from SDAccel environment. Now let's take some time to go over some recommendations and best practices to keep in mind as you design your RTL kernels. We'll look at performance optimization when accessing global memory using AXI-4 interface, considerations for achieving good QOR, and debug and verification considerations. Let's start with some tips and recommendations for optimizing AXI-4 memory performance. The AXI-4 bandwidth contributes significantly to the overall memory performance of the design. It is recommended that you make the AXI-4 interface to be 512 bits if you want to maximize the memory bandwidth for a native 512-bit wide memory. Other things to keep in mind are avoid the use of wrap, fixed, or subsized bursts. And when sending large amounts of data that is linear and sequential, send them in 4K byte bursts. This increases the efficiency of the memory controller. Avoid using deasserted write strobes. And take advantage of the split transaction bus architecture of the AXI protocol by pipelining your AXI transactions. Also, avoid using threads or AXI IDs that can consume additional resources unless it's absolutely needed. Try to avoid blocking the memory controller by requesting data that it cannot accept or generating a write transaction where it cannot deliver the data. And explicitly declare read-only or write-only interfaces. This will save logic. Now let's look at some recommendations to help improve the timing and resource utilization for your RTL kernel. Try and pipeline the reset inputs and distribute the reset as a tree to minimize the fan-out on the reset. Only the minimal number of essential flip-flops should be reset. The data path flip-flops on the FPGA do not need to be reset as they will come up in a node state. However, the control logic should be reset to ensure safe state. Always register the input and output signals where possible. The recommendations in the ultra-fast design methodology guide should first be applied at the RTL kernel level before integrating the design at the system compile level. Another tip is that XOCC can be run with the -S option to save temp files, allowing you to open the Vivado project standalone. And always aim for functional correctness of the design first by lowering the target clock frequency before optimizing the design for the target clock frequency. For designs that have a very high resource utilization or are pushing the clock frequency to the max, it is important to have an understanding of the floor plan of the FPGA. The VU9P device on the F1 platform contains 3 SLRs or dies connected using SSI or stacked silicon interconnects. The placement of the kernels should be such that they are each confined to a single SLR region. Logic that crosses SLR boundaries will have lower performance. Also, consider the location of the DDR channels and use map connect to connect kernels to the nearby DDR channels. You can provide the placement information through placement constraints for the kernel using XOCC options. Finally, let's look at some debug and verification considerations. You should do as much of your testing as possible at the RTL kernel module level by itself. Run exhaustive tests in a simulation environment as it gives greater visibility. Make sure the kernel is fully tested and verified and is AXI protocol compliant. Then make sure you can run hardware emulation on the design to test the integration and view the interaction between the kernels. Remember, don't rely on the hardware emulation for functional verification. It's mainly an integration test and not a functional test. Let's now look at the steps involved in creating an FPGA image for AWS F1, starting from the RTL kernels that we have built. The creation of the FPGA image consists of 2 parts. In the first part of this flow, we have SDAccel project, where we specify all of the inputs to the SDAccel compiler or XOCC. The inputs to XOCC include the RTL kernels, the platform or the F1 shell, and design constraints including kernel clock frequency. The compiled output from XOCC is the FPGA binary, which is the XCL bin file. In the second part of the flow, we take the XCL bin FPGA binary and convert it into an encrypted Amazon FPGA image, or AFI. The AFI is uploaded and securely stored on the AWS F1 storage. And a corresponding AWS XCL bin file containing the AFI ID is generated to reference the AFI stored in the AWS storage. Now let's look at the FPGA binary creation process in the SDAccel flow using XOCC. This process comprises of the platform assembly step, where one or more RTL kernels are integrated with the AWS F1 shell, and the FPGA synthesis and place and route step to produce the XCL bin bitstream. During the assembly step, the SDAccel compiler instantiates the RTL kernels and the F1 shell, providing all the needed interconnect logic to connect the AXI-Lite interfaces and the AXI memory mapped interfaces for the global memory. A Vivado project is generated for the assembled design with constraints passed for synthesis and implementation of the FPGA design. SDAccel automatically invokes Vivado to run RTL synthesis and place and route on the assembled FPGA design to produce the FPGA binary. This is generally an iterative process involving the analysis of timing and area reports from Vivado and optimizing the design to meet the performance requirements of the design. The ultra-fast design methodology guide provided by Xilinx is a document of best practices for FPGA design. The recommendations from this guide should be followed when designing the kernel for optimal results. Now let's look at some of the basic command line options that are commonly used with the XOCC command. The XOCC command takes one or more RTL kernels as input in the form of XO files. The first example shown here shows the command line options used to generate an XCL bin output using a single XO kernel targeting the AWS VU9P F1 platform. The second example shows the syntax for the XOCC command when building a design using multiple XO kernels. The target option in the XOCC command selects the execution mode for the compiled application. For the build flow using RTL kernels, you should first target hardware emulation to review the performance estimates of the kernel. Then you will need to target the hardware system to create a build that will be run on the FPGA. Note that the software emulation option is not supported in the RTL kernel flow that we are discussing in this case. The output of the XOCC command is an FPGA binary with the XCL bin file extension. The FPGA binary is produced after RTL synthesis and place and route using Vivado and can be found in the SDAccel project directory. XOCC also creates a Vivado project that can open in standalone Vivado environment to analyze and optimize your design to meet timing constraints and achieve desired performance targets. As you analyze and debug your design, you will want to look at the log files generated by Vivado during the synthesis and implementation steps. Also, the timing reports from Vivado are valuable in analyzing and fixing critical paths in your design during the optimization stage. Now let's talk about the kernel clock frequency and kernel clock frequency scaling feature in XOCC. What you need to understand here is that the clock that is used to drive the kernel is software programmable. What this means is that the runtime can run the kernel at a scaled clock frequency rather than a fixed clock frequency. If your design does not meet the specified target clock frequency when XOCC calls Vivado to synthesize and place and route your design, the runtime will execute the kernel at the lower clock frequency, thus meeting timing on the implemented RTL. This ensures that the design is not run out of spec by overclocking it. What this also means is that the actual performance of the design may be lower if the required performance was dependent on meeting the target clock frequency. Hence, it is important to keep this in mind when designing your system and account for the impact of clock scaling on your performance. Shown here is the syntax for specifying the target kernel clock frequency. The platform provides a default clock frequency for the kernel, which will be overridden by the frequency passed to XOCC using the --kernel_frequency option. When you need to work on meeting the target clock frequency or further optimize your design, you'll want to bring up the project in Vivado. In Vivado, you'll be able to use various optimization techniques to improve your design for timing and QOR. Again, use the guidelines recommended in the ultra-fast design methodology to optimize your design. The constraints used to achieve the optimized design can then be captured and passed to XOCC during the command line flow. Shown here is an example XOCC command with additional options to control the physical implementation of the design. The Vivado synthesis and implementation options are passed through a tickle file using the -xp switch. The tickle files may contain additional timing constraints or placement constraints. The example also shows how the effort level for different Vivado implementation steps can be directly provided on the command line through directives when calling XOCC. Next, we will look at Map Connect. For every AXI interface, we need to specify which DDR channel it should be connected to. The specification has to be done for the AXI interfaces of all of the kernels in the design. The default mapping, when no Map Connect information is specified, results in all of the AXI interfaces being mapped to DDR channel 0. So, in your design, if the bandwidth needs to be spread out between the DDR channels to balance the load, you will need to use the Map Connect feature to bind individual AXI ports to specific memory controllers. Shown here is an example design with 3 kernels, each of which connect to the global memory through an MXE port. The schematic shows the default binding of the AXI ports on the 3 kernels to a single memory controller. This may work well for some designs where the bandwidth provided by a single memory controller is sufficient to meet the design performance. However, for designs where we need to optimize a design for memory bandwidth, we can use Map Connect to allow binding specific kernel AXI ports to specific memory controllers. In this example, the Map Connect command line options and the resulting schematic are shown for the case where each AXI port from the 3 kernels are connected to 3 separate memory controllers. Finally, we will look at the second part of the FPGA image creation flow, where we take the FPGA binary and convert it into an encrypted Amazon FPGA image, or AMI. The creation of the Amazon FPGA image is done using command line utilities provided by Amazon on AWS. The XCL bin file, which is the FPGA binary, is converted into an Amazon FPGA image and securely stored on AWS AFI storage. A unique AFI ID is generated to access the AFI from the AWS storage. The AWS XCL bin file that's produced contains the generated AFI ID and can be shared with application developers without providing direct access to the actual RTL IP. The encrypted AFI resides in the AWS storage and cannot be accessed by the application developers. Let's quickly review some prerequisites for the AFI creation to work. Before you can execute the commands to create the AFI, you will need to have an Amazon S3 bucket set up in your AWS account. You can find detailed instructions on setting up S3 bucket on the AWS FPGA GitHub page. Within this S3 bucket, you'll need to create 2 folders: the DCP folder for the XCL bin and the logs folder for the generated log files. With this setup in place, we are now ready to create the AFI. Now we have the XCL bin ready for conversion to an AFI. The generation of the AFI is done by calling the create SDAccel AFI.sh utility with the switches shown. Create SDAccel AFI.sh takes the XCL bin file as input, performs a set of steps that are part of the AFI generation process. The XCL bin gets split into 2 parts, the DCP and metadata. A manifest file is created that sets the kernel clocks based on the achieved frequency of the FPGA build. It then calls the AWS EC2 create FPGA image. And finally, a new XCL bin called AWS XCL bin is created, composed of the metadata in XML and the AFI ID. To obtain the AFI ID or the FPGA image identifier, open the file with the suffix AFI_ID.txt that was produced by the create SDAccel AFI.sh. Shown here is the content of an example AFI ID.txt file where you can find the AFI ID highlighted in red. This AFI ID can now be used to manage the AFI using the AWS EC2 CLI commands and the AWS SDK APIs. Although the AFI ID is available immediately on execution of the create SDAccel AFI.sh script, the AFI generation process will continue in the background until completed. To check the status of the AFI generation, you can use the describe FPGA images API and provided with the AFI ID that was created and returned by the create FPGA image. Once the AFI generation is complete, the code status will change from pending to available as shown in the example. At this point, we have successfully generated an Amazon FPGA image that can be leveraged by app developers to accelerate their applications. Here are the steps to load and test the generated AFI on F1. You will need to start an F1 instance and open a new shell. You will need to have the compiled host code, executable file, and the AWS XCL bin file on the F1 instance. These files may need to be copied to the new F1 instance if they were compiled and generated on a different instance. Make a backup of the .xcl bin file as it will get replaced by the AWS XCL bin file. Finally, rename the AWS XCL bin file to have the .xelbin file extension with the original name. This step is needed because the host application looks for the original .xelbin file name. However, it will now reference the renamed AWS xelbin file when launched. We have now covered the tools, processes, and steps involved in packaging the RTL IP into a kernel and then integrating into an F1 shell to produce a bit stream and converting it into a secured AFI. Let's summarize what we have covered in this training. The SDAccel development environment enables RTL developers to easily integrate RTL kernels into an application running on a host computer that communicates with the FPGA through the PCI interface. The RTL kernels used to build the system in SDAccel need to conform to certain interface requirements. The RTL Kernel Wizard simplifies the process of adapting an existing RTL IP or creating a newer RTL IP to have the correct interfaces for the SDAccel flow. The RTL kernels are integrated with the F1 shell and synthesized to produce an FPGA binary, which is then converted to an encrypted Amazon FPGA image or AFI. More information on the SDAccel development environment and the RTL Kernel Wizard can be found online. You can also find a video demo of the RTL Kernel Wizard on the Xilinx website. This concludes the packaging and integration of the RTL IP for Amazon AWS F1 training video. Thank you for watching.